Welcome to Maths with EJD. In this video, I'll be talking about Markov chains. Straight to the point, a Markov chain is a mathematical system that undergoes transitions from one state to another within a finite or countably, within a finite or countably infinite set of possible states. It is a type of stochastic processes, of stochastic process rather, of stochastic process. Of course, stochastic process means random process. Random process. Random, you can also say probabilistic process if you like. So it is a type of stochastic process or random process. And what makes it special is that it adheres to the Markov property. This property states that the future, the future, the future state of the system depends only on the present state, only on the present state, not on the sequence of events of events that preceded it. So in simple terms, in a Markov chain, what happens next depends only on where you are now. Not how you got here. So by way of illustration, right, let's assume that you were at a point one, and then you got to a point two, and then you got to a point three, and then you got to a point four, right? So what the Markov property is saying is that the next point you're going to go to after point four, right, is determined by point four, not so it has nothing to do with all the previous points, one, two, and three. So the next point you're going to go to after point four is totally determined by point four. So whatever happened before point four is inconsequential. So where you're going to next is solely determined by point four. So that is the idea of the Markov property. So there's no memory about the past up to the only thing is your future is determined by your current situation, not how you got into the current situation. So that's a simple way to explain the Markov property. Okay, and that's what Markov chain is about. So it's about transitions from one point to the other, where the next point is determined by your current point, not how you got to the current point. So let's see some key concepts on Markov chains. Key concepts. So one concept is we talk about states, right? Talk about states. So states actually represent possible conditions. They represent possible conditions or outcomes of the system. So that's what state is about. Then we have transition probability. Transition probability. So the probability of moving from one state to another. That's simply the transition probability. So what's the probability that you move from this state to another state? That is what transition probability is simply about. And we also have what we call the transition matrix. Transition matrix. Transition matrix. You know, I always have this running issue with matrix and matrix. So I'm used to matrix, but it looks like the correct thing is matrix. And I have a matrix police always reminding me. So transition matrix. So a matrix representing representing a matrix representing all possible transitions, all possible transitions in the Markov chain, in the Markov chain. That is the transition matrix. Okay. So that's that. And of course, we have what we call the stationary distribution. Stationary distribution. Stationary distribution. So it is a distribution over states where once reached, the system stays in that distribution. Okay. Now let's talk about the formal definition of a Markov chain. So let's talk about formal definition. Of course, by formal, we'll be talking about a mathematical definition. So formal definition of a Markov chain. So imagine that we have a sequence of states, a sequence of states, S1, S2, S3, and so on and so forth. So the Markov property states, it states that the probability of getting to xn plus 1, of course, where the random variable xn plus 1 is the same thing as xn, small xn plus 1, given that you have been at xn equals xn, big random variable big xn equals small xn, comma xn minus 1 equals small xn minus 1, all of that up to random variable x naught equals small x naught, you know. So this probability, right, is equal to the probability. This probability is simply equal to the probability that you get to xn plus 1, random variable, equals small xn plus 1, given that you have only been at big xn equals small xn. So it means that every state you have been to, of all the states you have ever been to, what matters for getting to xn plus 1 is only xn. That is what the Markov property is all about. That's the only thing consequential to your next state is your current state, as you said earlier. So this implies, of course, you can see that xn is your current state, xn minus 1 is the state before that, and xn minus 2 up to x0 are all the states you got before you got to the current state. But of all of that, the only important thing that determines your next state is your current one. That's the Markov property. So this implies that the probability of moving to the next state only depends on the current state xn. Okay. All right. So having settled that, let's move on to types of Markov chains. Types of Markov chains. Okay, so one, we have the discrete time Markov chain. Discrete time Markov chains. Markov chains. So call that DTMC, discrete time Markov chains. Okay, so here, transition occurs at discrete time steps. Discrete time steps. So when we say something is discrete, right, it is countable. So you can move from 1 to 3 to 7 to and all that. That's discrete. Then number 2, we have the continuous time Markov chains. Continuous time Markov chains. That is CTMC, continuous time Markov chains. And that is here, transitions occur continuously over time. Continuously over time. That is discrete continuous time Markov chain, CTMC. And of course, we have number 3, which is the ergodic Markov chain. Ergodic Markov chain. That's ERGODIC Markov chain. Markov chain. Well, I don't know. I don't know if you can call that EMC. Okay. So this is actually a chain. Is a chain that is both aperiodic. Is both aperiodic and irreducible. Both aperiodic and irreducible, meaning it can eventually reach any state. It can eventually reach any state from any other state. Okay, so that is the ergodic Markov chain. Now let's talk about examples of Markov chains. Examples of Markov chains. So examples of Markov chains. So one, we have weather prediction. Weather prediction. Okay. Imagine a system where the weather can either be sunny, S, or rainy, R. Okay. And the weather of the next day only depends on the current day's weather. Okay. So here, going by the things we talked about before, what are the states we have? So we have just 2 states, sunny, S, or rainy, R. Those are the 2 states we have. Now, let's imagine that the transition probabilities are the following. Transition probabilities. So transition probabilities. So imagine that probability that if today is sunny, tomorrow is going to be sunny is 0.8. That's 80% chance. And what is probability that sunny, if today is sunny, tomorrow is going to be rainy? Let's say that is 0.8. So what is the probability that if today is rainy, tomorrow will be sunny? Okay, that is 0.4. Of course, this may be hypothetical, but you can actually get this idea from if you have data for a very long time, you can actually decipher these probabilities. So probability again that if today is rainy, tomorrow will also be rainy is equal to 0.6. So now you can see that if looking at when rainy is the current state, where it finally goes to. Okay, I think I made a mistake here. So this should be 0.2 here. So if the starting point is sunny, so we can look at both together as a whole, So if it's sunny today, what's the probability that it will be sunny tomorrow? So if you add that probability to probability that if today is sunny, tomorrow will be rainy, that should give you 1, which is the total maximum probability you can ever get. Okay. So rainy to sunny, rainy to rainy, those two probabilities should add up to 1, just like sunny to sunny and sunny to rainy. Okay. So let's assume that that's what we have, right? So in that case, we can put the transition matrix together. Okay. So we can now say that the transition matrix, the transition matrix, which you can call T, would look like this, would look like this. So simply with T equals, 0.8, 0.2, 0.4, 0.6. So it's more like you have, this is sunny. So this is like sunny, 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 rainy, sunny, rainy. So if it's sunny today, probability that it will be sunny tomorrow is 0.8. So let's say this is now, and this is later. Assume later is the next state. So if it is sunny now, the probability that it will be sunny tomorrow is 0.8. If it's sunny now, probability that it will be raining tomorrow is 0.2. If it's raining now, the probability that it will be sunny tomorrow is 0.4, as we have up there. So if it is raining and the probability that it will be raining tomorrow is 0.6. So that's what the transition probability simply looks like. So that's a very good example of Markov chains. So let's take another example. Let's say example 2. So we can apply this in board games, board games, like Monopoly. Okay. So you see that the movement of a player, the movement of a player on a Monopoly board can be modeled as a Markov chain. So the player moves from one square to another based on the roll of dice and the probability of moving of moving to any given square depends only on the current depends only on the current square. And the dice roll. That is assuming no special conditions like jail. Okay. So here, what are the states? What are the states? The states are the positions. They are the positions on the Monopoly board. So those are the states. The position on the Monopoly board are the states. Then we have the transition probabilities. So the transition probabilities are determined by the dice and game rules. Because that will be a lot, right? Then we can also talk about the stationary distribution. Stationary distribution. So for the stationary distribution, right? After a large number of turns, some positions like what they call jail in Monopoly will have a higher probability than others due to game mechanics. Well, the very virtue of how the game is defined, right? So that is for board games like Monopoly. Another example of Markov chains would be Google's PageRank algorithm. Okay. Example 3, Google's PageRank algorithm. So Google's PageRank algorithm Google's PageRank actually uses a Markov chain to rank websites. So it models the web as a graph where each page is a state and links between pages are transitions. The probability of moving from one page to another is based on the links, and a random surfer will either click a link or randomly jump to another page. So in this situation, we have the states. The states are basically the web pages. The web pages are the states. Web pages, these are the states. Then we have the transition matrix. So the transition matrix are based on the links between pages. Then thirdly, you have the stationary distribution. So you have the pages with the highest probability. In this stationary distribution are ranked higher by PageRank. Okay, so you can see some practical applications of these things. Okay, let's go to talk about um another example of Markov chain. That'll be the fourth one in this case. That is Markov text generators. Markov text generators. So a Markov chain can be used for text generation, where the next word depends on the current word. So you can see where the whole idea of predictive text comes from when you're typing on your phone. So, your phone has studied your typing pattern such that by the time you're typing, it already probably guesses the next word that it's going to follow, especially if there are some sentences you always use. So where the next word depends on the current word, or sometimes the current few words. So I mean, that's sounding to me like where the whole idea of predictive something connected with the idea of predictive text. So a simple Markov model can learn from a body of text and generate new text by sampling transitions between words. So in this case, what are the states? The states are simply words or sequences of words or sequences of words. Okay. And then we can have the transition probabilities. Transition probabilities. So here, the transition probabilities are determined. They're determined from the frequency of word sequences in the training text. For instance, the training text that determines the predictive text on your phone are all the the every kind of each time you're chatting, the kind of text you write, or when you're sending text messages and all of that. So the system learns it, and then if you for instance, most of the time when my birthday messages have a particular set of words, so I always get those words predicted back to me, because so that must be coming from this idea of Markov text generators. For example, for example, in the sentence, in the sentence, the cat sits on the mat. The next word, okay, the cat sits on the mat. The next word after the, the next after the might have a high probability, a high, a high probability of being cat based on past occurrences in the training data. And we also have queuing systems. That would be like the fifth example. We have queuing systems. So you can see Markov chains are really useful. Queuing systems. Queuing systems. So in queuing theory, this is tricky. In queuing theory, Markov chains can model customer behavior in systems like a bank or call center. Each state represents the number of customers in the queue, and the transition probabilities represent arrivals and service completions. Okay, so here the states are number of customers in the queue, number of customers in the queue. Then you have the transition probabilities. So that will be probability of customer arrivals and service completions. Okay, so well, this may look like overflogging the issue, but I like to talk again. Of course, we are talking about some applications now. Of course, the examples we've seen already can already suggest some kind of applications to us. But can we still talk about applications of Markov chains? Applications of Markov chains. So, course number one, we can have that in economics. In economics, we have that stock market modeling, stock market modeling, where the next market, where the next market state depends on the current state. And then, of course, we have the possibility of Markov chains in physics. Physics, so we can model physical systems, modeling physical systems like the movement of particles in a gas. And three, we have speech recognition. Hidden Markov models, hidden Markov models, what you can call HMMs, are used for speech and handwriting recognition and handwriting recognition. And of course, we have application in genetics. Markov chains are applied in genetics. So here you can use that for modeling gene sequences, and mutation patterns. Over generations. So in all, right, you can see that Markov chains are a versatile tool used in a wide array of fields for modeling systems where the next event, only depends on the current state. Okay, so with that, we come to the end of this particular video. Now you can see it's more of theory here, more of stories. So I'm going to make one more video on Markov chain where I'm going to take a worked example. That'll be the next video after this, so watch out for that. So if you have not subscribed to this channel, be sure to do that and hit the notification bell so you can always get alerted whenever a new video is released. Then don't forget to comment, like, and share. Then watch out for the next video, which is going to be on a worked example on Markov chains, and it will be about weather prediction. See you then. Bye.